So next speaker is Pedro Marquez from Juniper Networks. He's working at Juniper as an OpenContrail engineer, software engineer. He was actually a co-founder of this company before being acquired by Juniper. And most of you probably know Pedro from his extensive work in the standardization body and more particularly in the ITF with all BGP-related topics. Pedro, welcome.
Thank you. So I can do a BGP open source implementation in my garage, but I cannot control this thing. What's the trick?
We are complementary.
How does this work? Okay, and then if I control it, it will show up here. Okay. Arrow keys. Okay. Thank you very much. So today I'd like to talk to you about OpenContrail deployments in the carrier space. I'm not going to focus on the stuff we're doing in infrastructure as a service and software as a service fields because I think this audience is mostly interested in the carrier context. So I guess the first question is why? So, I mean, as you're well aware, in terms of carrier wireline, in the late 90s, early hundreds, early noughts, we start seeing the outsourcing of branch office connectivity by service providers. Large enterprise used to have frame relay circuit meshes, and these were replaced by L3VPN and later MPLS. Most people in the carrier space are looking at the moment at the opportunity to outsource network-based services the same way that connectivity was outsourced. We're talking about security appliances that are in the branch office, VPN in access, wireless controllers, CDN offerings. There's a lot of interest in looking at outsourcing all of those services. The part that is significantly different is the fact that we're now looking at competition with lots of over-the-top providers. I think if you look at security, you can think of somebody like Zscaler, which is over-the-top security. There's Meraki, will do over-the-top wireless. VPN access, you can find lots of over-the-top IPsec VPN. Most of these are small companies and startups out there. And what's common about those solutions is they're all self-provisioned, and a lot of times these companies have the ability to roll out new services faster. I think one of the things that most carriers are looking at is getting the right compromise where you can compete with those over-the-top providers but tie that service with the traditional service offerings they have within their on-net access. So OpenContrail. OpenContrail is, in the carrier context, a service delivery platform. It's an open source project licensed under Apache License V2, which in one of the things that it does is it grants you patent rights over anything that may be patentable in the code. So to address Jakob's point, Juniper Networks offers commercial support for OpenContrail, and it's the main contributor to the project. The main reason that made us go open source with this product is that it makes it easier to integrate with a large number of tools that are open sourced in the ecosystem around. We often integrate with OpenStack, CloudStack, other orchestration systems that are either open source or our customer has access to. And if you think about nuts and bolts, you can think of an OpenContrail cluster as an L3VPN PE, except that instead of CE devices, you have service appliances. So think about a PE that has 10,000 service cards where you can run an arbitrary virtual machine in one of these service cards. That's pretty much what we're trying to accomplish here. The only major difference you'd see when interacting with a system like this is that there's no CLI. You cannot go and configure SEP protocols, BGP, blah. It's all API-driven management and typically driven through an orchestration system. So most people actually don't interface with Contrail directly. They do so through OpenStack APIs such as Neutron and Heat. So I couldn't talk about a particular deployment in this presentation, so I'm sort of taking the average of what most of the OpenContrail deployments look like. Typically, what we're looking at is deployments where there are multiple regions, and by a region I mean an independent failure domain that doesn't have any shared databases. Regions, however, can have multiple physical locations. So from a logical perspective, and again, if you're thinking about L3VPN PEs, each one of these regions would be a PE, and I would be showing a network with 2 PEs that are running service appliances. Within the region, however, there's a little bit more complexity, but you can assume that each region exposes a set of API endpoints that allow you to provision the services that execute on that region. And sort of to place ourselves in the stack, you can have you have a base layer below of compute, storage, and network, where OpenContrail also implements the basic networking for OpenStack, for instance. And I'm focusing on what OpenContrail is doing in terms of service insertion, which is a layer that will sit below issues such as the lifecycle management of the VNF and then the configuration management of the VNF. And you can also think then later of OSS BSS as the ultimate layer that will pay the bills. So as a logical diagram here, what I have is 2 regions. So coming back to that previous slide in terms of physical design, I have a logical model of 2 regions that are providing network access for customers sitting behind PEs. And in each region, we have modeled an access network that terminates a PE or a set of Ps, actually a CE or a set of Cs. And the software imposes a set of services, in this example would be firewall, to the next network on the chain, which is network in region A. Network in region A is then connected to an MPLS core to network in region B. So each of our regions work independently to assure that, for instance, in this example, all the traffic goes through a firewall between access and the MPLS core. By the same token, the traffic that has to go through the private peering endpoint in the top right corner would have to go through a service appliance on the other side of it. So service insertion, how does it work? Well, first let's look about how connectivity between networks works. If you look into basic L3VPN, if you want to connect virtual network red, which has a specific route target, and virtual network green, the simplest thing to do is simultaneously import the route targets. So once you have network red importing the route targets of green, you have connectivity, and the routing instance red has routes to routing instance green. That's basic L3VPN constructs. What service insertion does is modify the routes that are imported in order to adjust the next stops of the routes. So the way that services are imposed into the connectivity between networks is by looking at the routes of network green and re-advertising those routes with next stops that correspond to the multiple instances of a firewall. That way you can fan out the traffic to these virtual firewall. One of the nice things about this approach is that this will work whether network green and network red are within the cluster or completely external to the cluster. It's fully interoperable with L3VPN mechanisms. The other advantage of this approach is that scaling up and down the service, so inserting a service instance into this into the traffic between these two networks is a question of adding or deleting a next stop from the route. Of course, I'm showing in these slides just the left to right direction for traffic, but you have to imagine in the slides that this is duplicated. So, firewall is a symmetric service, left to right. The mechanism works for the opposite direction, right to left. The same mechanism is taken into account. So network green also imports a hidden network called red prime. The mechanism is composable, so you can have, in this example, you can have as a rule the intention to apply both firewall and DPI between traffic that flows in both directions, actually. And we just repeat the process. Routes, advertisements coming from network green get imported into green prime with modified next stops, get imported into green prime with modified next stops. If at any point in time you want to add or remove one of the firewalls, for instance, that doesn't affect the next stops that are exposed into the routes in network red. So you don't have the traditional problem that you have with, say, flow-based mechanisms where if the routing changes, you have to go and invalidate all the flows. Sitting above typically sits a workflow engine. This could be, in some of our deployments, it's Heat, could be UBCube or Cloudify or IBM SCO. And typically, on a per region basis, these have service catalog entries. An example is if the customer is looking for managed security, that means that whenever a CE is provisioned with managed security, there's the need to create and update an access network and connect that access network with the enterprise network through a firewall instance. So in here, typically the route target that the CE is attached to is one of the parameters. The route target of the enterprise network is another parameter. And then the service definition is a third parameter on this template. Most of these workflow engines, they're all different, but they have this ability to create a sequence of operations and track the resources that were allocated, because we want to know which virtual machines were allocated to this specific service catalog entry. One of the reasons that OpenStack Heat is often used or similar is because today Neutron doesn't quite provide a standardized API for service chaining. One way that several of our customers deal with that is by looking at Heat and creating templates which then would allow it to abstract the API calls with a different implementation if they so choose. In terms of overall lessons learned from the deployments we have so far, I tend to tell people, if you're doing a core network, you don't just go and buy 100 routers and throw them in a network. Typically, there's a long cycle with architecture review, design, validation, and then deployment. It's not unusual that a standard network takes a year or more to deploy as you go through all these design stages. this is, in a way, this area is not different. You do need to have an extensive test and validation stage in order to be able to deploy something. Within the structure of these systems, there's a fair amount of complexity. And one of the things I always recommend the people I interact with is that they automate the deployment stages so that later on when we're validating something, we can replicate the entire stack. You've seen probably in some of our slides, very commonly we're working with OpenStack, Ceph, OpenContrail, Heat, something else on top, a bunch of different VNFs. These are complex stacks, and it's very important to have a process that can guarantee that you test something, you can test the exact same thing the next day when you want to test a change. It's also very useful to have the concept of multiple clusters, test, staging, production, so you have a delivery pipeline around validation and build that through the start. In a way, I mean, when I compare it with traditional network design, yes, the tools are different. We're talking about typically using Puppet and Python as kind of standard tools instead of expect scripts. But in a lot of ways, the steps one needs to take are similar. You need to think through a project plan. You have to ensure that you end up with something that you validate and can reproduce when you want to change software. In a lot of times, the key issue here ends up being one of project management, being able to set a set of reasonable goals quickly and be able to move towards these goals and work incrementally. And I think the people that I've worked with and have projects that are further ahead, they do so because they've done a great job of putting a team together around a set of common goals and managing that project. The people part of things ends up being harder than technology a lot of times. So that's pretty much it.
Okay. Thank you, Pedro.
You're welcome.
Any question for Pedro?
You're going to have to ask a question, Jean-Marc.
Any answer for Pedro? Any joke for Pedro? Okay, so, yeah, thank you. There is one question.
Hi.
Keep your applause energy for 30 seconds.
Okay, can you just explain why you do not work with Neutron and OpenStack?
We do.
You do?
Yeah, we implement the Neutron API. Is that just we have some extensions to the Neutron API for things that Neutron has not yet standardized.
Yeah, but I think it's OpenStack at all is going to be standard for cloud, something like this.
So OpenStack at the moment is sort of working as a de facto standard for cloud APIs.
Yeah.
This goes back to the conversation we were having before, and I guess the panel. But you know, there's a lot of popularity. People want the OpenStack API is good enough. I mean, it's a copy of the AWS API, and there seems to be rather strong adoption of that. Although, of course, not everybody agrees with the implementations of specific components, and OpenContrail is an alternative implementation of the Neutron API, but tries to be as compatible as possible with Neutron, although it does support extensions.
I think also, just to extend a bit the question, because I guess some other people may have the question in mind, what are the key attributes maybe missing in a native Neutron today that justify such an alternative option?
The service insertion functionality that I was describing does not exist in Neutron, and OpenContrail is natively an L3VPN implementation. So if your goal is connectivity to an L3 VPN network, there's certain things that are just natural. Under the covers, everything is an L3 VPN network. You know, it's a large L3 VPN-P where you can just have a very large number of service cards. That would be the best way I have to describe it.
Mm-hmm. Okay, thank you. Thank you very much, Pedro.
Thank you.